first subtopic here, 3.1, as you can see, is about momentum, Newton's law of motion. Okay, so first of all, let us go through Newton's law of motion. So we have the first law. If a body is at rest, it remains at rest. Okay, so this is the first case. If it is in motion, it moves with a uniform velocity. Okay, so until it is acted on by resultant force or torque. So that means, for example, if you put a book on a table, it will remain on the table until there is a force that pushes it, an external force that pushes the book. For example, also, if an object is moving in uniform velocity, it will remain in uniform velocity until there is an external force, there is a net force that change the uniform velocity. Then it will either accelerate, or it will decelerate, or it will change direction. Of course, torque will make rotation happens. So rotation happens because of the torque. So that is the Newton's first law of motion. Newton's first law of motion is related to inertia. Okay, inertia. You may have heard of inertia when we talk about first law of motion. So inertia is basically the resist of change in motion. So that is inertia. Okay, so and inertia is affected by mass. Inertia is affected by mass. So for example, let's say we talk about two objects with different mass. So let's say a light marble and a big stone, heavy stone. Okay, so for the marble, let's say it is at rest. You want to make it move. It is easy to make it move. Okay, so if a big stone, it is at rest. You want to make it move. It is hard to make it move. So that is the idea of inertia. But once they are moving, once the marble and the stones are moving, so it is hard to make them, when they are moving, you want to stop them. So for the marble, it is very easy to stop it because it is having low mass. Okay, so but for the big stone, you want to stop it, it is hard. Okay, you need more effort to stop it. So the mass affect the inertia, and inertia is closely related to the first law of motion. Something at rest will remain at rest. Something at rest, you want to make it move, you need force. Something which is in moving, it remains moving. You want to stop it, you need force. So that is first law. Now we look at second law. The rates of change of momentum. The rate of change of momentum. So first change of momentum is mv minus mu. Final momentum minus initial momentum. And when they say the rates, right? So it's basically where you need to divide by time. And divide by time, then it becomes rates of change of momentum. It's proportional to the resultant force. So proportional to the resultant force. And through experiments, we realize that they are equal. Okay, they are equal straight away. And after that, we factorize the m. Then we have v minus u over t. And then we know what we have in the bracket is accelerations. So we can change this to ma. So that is how we get the formula. Okay, so the formula. Sometimes you may see the second law. The second law is given in this particular way. A equal to F over M. Okay, F over M, where they put second law as acceleration is proportional to force. Acceleration is directly proportional to force. That means the greater the force, the greater the acceleration. So acceleration is inversely proportional to mass. The greater the mass, the lower the acceleration. Something heavy could hardly accelerate. So you can see second law in this way sometimes. And this is one version. This is another version. Okay, so now we look at third law. If a body A exerts a force on a body B, then body B exerts an equal but opposite force on body A. So we have action-reaction pair. Okay, so let's see the example again. Here, we put an object on the ground, m kg. Okay, so it has weight which act downwards and pressing the ground. So the weight is mg. Okay, mg. And this is called action. So the action is the weight is pressing the ground. But you don't see the mass sink downwards. That is where the ground hold back the mass here, the object here. So they have a force which hold it. So this is called the reaction. We call it normal reaction. Normal reaction. Sometimes you can see they use N. Sometimes they may use R to represent the normal reactions. Okay, which have the same value as mg, but it has opposite direction. Okay, opposite direction. Now this is acting upwards, but the value, the magnitude is the same. It is also mg. So it's also mg. Okay. Now, these are the three laws, and of course, I'm trying to say another example also. Let's say, for example, this is the wall. If you are pressing the wall with a force of 200 Newton, so this is known as the action. Okay. You are pressing the wall with 200 Newton, this is action. But the wall is not moved by 200 Newton. Okay, so the wall hold you back by having the normal reactions, which is 200 Newtons, same magnitude with the action. So this is the R. Okay, so reaction. So this is where the Newton third law happens. Okay, now we look at the next subtopic, mass and weight. So mass, measured in kilograms, is a scalar quantity constant throughout the universe. So that means wherever you go, whichever planet you go, so the mass is still the same value, how many kg. Okay, so what is actually mass? Mass is amount of matter in the body. So it's the amount of matter in the body. So that's why it is constant throughout the universe. Okay. Now, compare with weight. Weight is the force of gravitational attraction. So it's affected by the gravitational force. Different planets have different gravitational force. So because of that, the weight is not constant. Different place, different weight. So measured in newtons, it's a vector quantity. It has direction which act downwards. It's not constant. Okay, in this planet, we have this weight. In another planet, on the moon, we have different weights. So the formula W equal to mg. Okay, so now we look at mass again. Mass is a measure of the amount of matter in the body and is the property of a body which resists change in motions. So this is inertia. Resist change in motion is inertia. So mass is a factor that affect inertia. So we discussed this just now. Whereas weight is the force of gravitational attractions exerted by the Earth on a body. So the Earth attract the object on the Earth. So it has weight because of that. So W equal to mg. Now let's move on. Momentum, linear momentum, product of mass and velocity. So the formula P equal to mv. P stands for momentum, mass times velocity. So that is linear momentum's formula. Now we have force, rates of change of momentum. So this one we saw it in Newton's second law just now. Okay, so force equal to mv minus mu over t. Okay, so we look at the next subtopic. After 3.1 supposed to be 3.2, but I do 3.3 first because it's just continue from 3.1. Okay, so 3.3 we focus on the principle of conservation of momentum and the formula. Okay, now let's see. Principle of conservation of linear momentum. When bodies in a system interact. So how they interact? For example, collide. The two bodies collide. Collisions happens. So total momentums remain constant. That means total momentum before collisions is equal to total momentum after collisions, provided no external force act on the system. No external force. So this is the one. MAUA plus MBUB. So this is total momentum before collision. Before collision is equal to total momentum after collision. Okay, so this is the formula, and let's move on first. You can see how we use the formula very soon in the following examples.
Let us look at this part. Applications of momentum in elastic collisions. So what is elastic collision? So in order to understand this, it is good to separate the collisions into these situations. So first, collisions is subdivided into perfectly inelastic, followed by perfectly elastic and inelastic and explosions. Okay, so we will go through each types of collision one by one. So the first type, perfectly inelastic. So what happened here is two objects collide and stick together. That is perfectly inelastic, so they will stick together. So what happened is momentum is conserved, kinetic energy is lost. Okay, so since they stick together, we can use our principle of conservation of momentum in this particular way. So you try to imagine, I draw out the pictures. So you have object A, object B. So let's say they are moving with UA, UB. So after collisions, they stick together and move with the common speed of v. So we can use the principle of conservation of momentum in this way. ma ua plus mb ub equal to ma mb times v. So where on the right hand side we can add up the masses and multiply with the velocity. Okay. So the second situation, we have perfectly elastic. The situation here is two objects collide and bounce off one another. So in this case, momentum is conserved and kinetic energy is conserved. Now, for the formula, of course, we can use MAUA plus MBUB equal to MAVA plus MBVB. So we can use this formula. Okay. Now let's move on. In elastic collisions, two objects collide and bounce off one another. Again, momentum is conserved, kinetic energy is lost. So for the principle of conservation of momentum, again we can use MA UA plus MB UB equal to MA VA plus MB VB. Explosions. So explosion is actually perfectly in elastic collisions in reverse. So imagine that the two objects stick together at the beginning. As you can see here, they stick together. After collisions, they will separate. Okay, so let's say I draw pictures here. So we have A and B that stick together. So after that explosion happens, they are separated in two different ways. So this is explosions. So since they are together at the beginning, so we can use MA plus MB multiply with U. So after that they are separated, then we count the momentum separately. Okay, so that are the principle of conservation of momentums for the four situations here. Okay, now let's move on with the notes. When you see the notes, they say total momentum conserved, total kinetic energy is conserved. So it is actually referred to this type. Okay, it's actually referred to this type, perfectly elastic. Momentum is conserved, kinetic energy is conserved also. Okay, it's under perfectly elastic. Total kinetic energy is conserved. So how to take this idea? Total kinetic energy is conserved. So for example, we can use this formula: 1/2 ma ua square 1/2 mb ub square equal to 1/2 ma VA square plus 1 over 2 mb VB square. So the kinetic energy is conserved. Okay, now let's move on. Example, two identical spheres collide elastically. Initially, x is moving with speeds v and y is stationary. What happens after the collisions? So when I said collide elastically, that means if you see the four types here, so it is under the perfectly elastic actually. So the momentum is conserved, the kinetic energy is conserved also. Okay, so you see the answer here. X stops and Y move with speed V. So it seems like they are exchanging their speed. Okay, they are exchanging their speed, and then because of that, the kinetic energy is conserved. Okay, kinetic energy is conserved. Okay, so this is under perfectly elastic collision. Of course, if we want to work out the calculation, it is going to be like this. Okay, so the calculation is going to be like this. Before collisions, the total KE is equal to 1 over 2 mv squared plus 1 over 2 m0 squared. Okay, so what happened here is object x, velocity v. Object y, it is stationary. So that's why the velocity is 0. Okay, so if I simplify this, I will get 1 over 2 m v squared. Okay, so observe that I'm using the same math for this because the question is saying identical sphere. Okay, so after collisions, the total KE 1 over 2 m0 squared 1 over 2 mv squared. So from the answer given here, they are exchanging the speeds. So the first object stops, the second object moves with speed v. So the total kinetic energy is this, and if I simplify it, I will get 1 over 2 mv squared. So from here, you will realize that total kinetic energy before collisions is equal to total kinetic energy after collision, and this is under the second type, perfectly elastic. So when I say elastic collision, that means it is perfectly elastic collisions. Okay, so next formula, relative velocity before collisions equal to negative relative velocity after collisions. Okay, so it means UA minus UB equal to VB minus VA. So this is a valid equation for perfectly elastic collision only. So as you can see here, perfectly elastic collisions, we have already we are having two formula already. So the conservations of momentum, conservations of kinetic energy. Now we have the third one which is UA minus UB equal to VB minus VA. Okay, so that is the third formula, which is for perfectly elastic collisions. Okay, so for example, let's say I use these as my example, and let's see how we do the calculation for UA minus UB. So UA minus UB, okay, so UA is V, UB is 0, so I get V. VB minus VA, okay, so they are exchanging the speed. So VB is V now, and then VA is 0. Okay, so from here you can see they are same. So that means these two can equal to each other. And this formula is correct for perfectly elastic only. Okay, now let's move on. Applications of momentum in elastic collisions. So what we can see here, relative speeds of approach is greater than relative speeds of separations. So that means our formula is UA minus UB is more than VB minus VA. Okay, so this is for inelastic collision. So the inelastic collision here can be the perfectly inelastic or inelastic collisions. So let's see here. Perfectly inelastic collision. So this is the one that we mentioned just now. The objects stick together after collision. Only momentum is conserved. Kinetic energy is not conserved. And relative speeds is going to be more than in this way. And kinetic energy is also not conserved. Okay, so the particles stick together after collisions. Example, that means move with the same velocity. So we already discussed the formula that can only applied to perfectly inelastic collision is the conservations of momentum, which is this way: MAUA plus MBUB equal to MA plus MB times V. Okay, now let's move on. Inelastic collisions. So the inelastic collision here refer to the two objects which collide and bounce off from one another. Okay, so that is the inelastic collision. Total energy is conserved, but kinetic energy may be converted into other form of energy, for example, heat. Okay, so that means only principle of conservations of momentum is applicable. So we can only use this formula, MAUA plus MBUB equal to MAVA plus MBVB. The kinetic energies equation, we cannot use it, and the relative speeds of approach is not applicable also. They are not equal, they are greater than as well.
Okay, a glider of mass 0.20 kg on an A track is moving at 3.6 meter per second towards a second glider of mass 0.25 kg, which is moving at 2.0 meter per second in the opposite direction. So when I say in the opposite direction, I have to put negative sign for this. When the two gliders collide, they stick together. Calculate their joint velocity after the collisions. Okay, so we need to know that if they stick together, right? You see our formula is MAUA plus MBUB equal to MAVA plus MBVB. So imagine that VA and VB are the same velocity. So at the end, you can just factorize the same value from here. Imagine this is V, this is also V. Then you can factorize the V from the two terms over there, and it become MA plus MB V. So normally we will put it in this way, which makes the calculation a bit easier for inelastic collision. So normally we put this way. Now we substitute with value 0.20, 3.6, 0.25. Since this is opposite direction, I put negative 2.0. MAMB is 0.20, 0.25, multiply with V. And then you go and count V, you get 0.25. 0.49 meter per second. Okay, now B. Show that the collision is inelastic. Inelastic. Okay, so you can use this. You can show that this is greater than this one. Okay, so we can do something like this. UA minus UB. 3.6 minus negative 2.0. 5.6. VB minus VA. So since they have the same velocity, right? So it should end up with 0. It's 0.49 minus 0.49 equal to 0. Okay, then at the end, we can say that UA minus UB is more than VB minus VA. And hence, inelastic. Okay, so that is how we do it, how we show. And let's see the past paper here. Two railway truck of masses M and 3M move toward each other in opposite directions with speed 2v and b, respectively. 2v and b, but you have to know that since they are in opposite direction, this should be negative v, this one 2v. Okay, so this truck collide and stick together. What is the speeds of the trucks after the collisions? Okay, so we just count it. M, 2v, 3m, negative v. So since they stick together, we add up the masses and find out the velocity 2, let's say. Okay, then we just add up 2mv minus 3mv. We get negative mv, 4mv2, cut the m. So v2 equal to negative 1/4 v. Okay, but they ask for speed. What we count here is velocity, yeah. So they ask for speed. So the speed is 1/4 v. So the answer is A. So we do it like this. Okay. Now let's move on. 3.2. Non-uniform motion. Non-uniform motion. So you see the words here. A body falling in a uniform gravitational field will experience a constant weight as the strength of a uniform gravitational field is constant. Okay, so the weight is constant. They are trying to say that. Below is a description of the motion of an object with an initial velocity of 0 meter per second in a uniform gravitational field. Okay, so it fall down, that means the object fall down. The object has constant weight. So imagine it's something like this. You have an object. The weight is W. W is constant. The object experiences weight downwards and air resistance upwards. So air resistance is upwards. As the magnitude of weight is larger than air resistance, it will accelerate downwards as there is a resultant force. Newton's second law. So they're trying to say something like this. The net force or the resultant force is W minus air resistance. Okay. So at the beginning, of course, air resistance is having a very small value. So because of that W minus AR, you end up with some values. Okay. And because of that, based on Newton's second law, net force equal to ma. So if this minus this, you end up with some values, then they will have accelerations. If this minus this end up with 0, then acceleration is 0 also. So this one is more than 0, and then this is more than 0. That means the object accelerates. So as the object's velocity increases, so imagine they are this object is accelerating, and hence it's getting faster and faster. So when it's faster and faster, the magnitude of A resistance increases. So A resistance is affected by velocity. So the object is moving faster and faster. And now this is getting greater and greater. So therefore, the resultant force and acceleration downwards will decrease. Okay, so try to imagine that this is getting bigger and bigger. So W minus a bigger value now, end up with a smaller answer. Then the acceleration will become smaller. So acceleration decrease. Air resistance will continue increasing up until the point where the magnitude of weight and air resistance is equal. Okay, so when W minus AR and you get equal to 0, then based on Newton's second law, A is also equal to 0. So there is no resultant force. When this equal to 0, that means the net force is 0. When there's no resultant force, the objects will have no acceleration and it will move at constant velocity, and we call this terminal velocity. So the graph is like this. The gradient represents the acceleration. You can see the gradient is like this. Then the gradient decrease and decrease and decrease. So the gradient decreases to 0. When it's 0, then it has terminal velocity. So this is something that we talked about before. Let's just move on. Air resistance will affect both the vertical and horizontal component of a projectile motions. So this one we discuss also in the projectile's motions. So air resistance will affect both the vertical and the horizontal component. So without air resistance, the projectile motion seems to be able to go higher and further. With air resistance, it don't go that high and it doesn't go that far. So as you can see, with air resistance, the maximum height is reached earlier, and the vertical and horizontal distance traveled decreases. So that is the effect of air resistance. Okay, so we have done the theory part for dynamics. Okay, now let us practice. Question on page 9. A shopping trolley and its contents have a total mass of 42 kg. The trolley is being pushed along a horizontal surface at a speed of 1.2 meters per second. When the trolley is released, it travels a distance of 1.9 meters before coming to rest. Assuming that the total force opposing the motion of the trolley is constant, calculate the deceleration of the trolley. Okay, so we have to use the what formula to do that. So we have the displacement 1.9. We have the initial velocity 1.2, and we have the final velocity 0. So we want to find the A. So based on all these informations, we don't know T, so we have to use this formula: B squared equal to U squared plus 2AS. 0 square, 1.2 square, 2a, 1.9, 0, 1.44, 3.8, a. Okay, so we count the a. Minus 1.44 over 3.8. So we get negative a equal to negative 0.379 ms negative 2. So when you want to put it in deceleration, you can just remove the negative. 0.379. Okay, so that's how we do it. And part 2 showed that the total force opposing the motions of the trolley is 16 Newton. So what to do is we use Newton's second law, F equal to ma, where the F is the net force or the total force. Okay, so this is the total force. Okay, I put a T there to represent total. So total force, we don't know. We know the mass, 42 kg. Then we have the deceleration, 0.379. If you put acceleration inside, you end up with negative value. It's just fine, you know. Okay. It just shows that the opposing force is acting in opposite direction. Okay, but putting this can avoid the problem of getting negative. Okay, so we just take 42 multiply with 0.379. Then we get 15.9. So we round off to 16. 16 Newton.
Teacher.
Yeah.
If they say the opposing force is constant, does that mean that the deceleration is constant?
Yes. You know, they are related straight away. If it's constant, then this will be constant. Okay. And look at B. Using the answer in A part 2. Calculate the power required to overcome the total force opposing the motions of the trolley at the speeds of 1.2 meter per second. Okay, so for this one, in order to find the power, we need to know power equal to, you see in A part 2, we have force. Okay, we have force. So for the power formula, you may think of power equal to energy over time. This is one of the formula. You may think of power equal to voltage times current. Okay, so but over here, in order to use A part 2, we can't use these two versions. We have to use power equal to force times velocity. Force times velocity. So force multiplied with velocity, 16 multiplied with 1.2, then we get 19.2 watt. So that's the value of power. 19.2.
Why can I use work done over time?
Work done over time. Because they say use the answer in A2. So that's why we use 16 Newton to continue. 16 Newton.
But like, if you use work done over time, can you use force times the distance, which is 1.9, then you divide by time.
So that means you are trying to consider it in this way. Work done over time, force time displacement over time. So at the end, displacement over time is just velocity.
Oh, so it doesn't matter one.
Doesn't matter. End up with the same answer. Okay.
Oh,
Yeah, so that's why we have force time velocity coming down, coming here in the southern because of that same concept. Okay, now let's continue. We look at C. So that makes the situation a little bit more complicated. The trolley now
wait,
moves
teacher,
up. Yes. Yeah.
if I use like the previous question, if I use the other formula, right, then my final answer will be different or no?
Oh. So okay, let us see. Why it's different. What value you put for your force?
16.
16. Okay, let's see. We do it down here. 16. Do you substitute the displacement?
Yeah, 1.9.
1.9. Okay. So you are using the displacement here. 1.9. Okay. Then what time you put?
I use the acceleration and calculate. Cause is uniform deceleration.
Okay. So you count the time. Okay. So that means you are doing something like V equal to U plus AT, is it, to find the time?
Yeah.
Okay, let's see. If I put in so the time that I'm going to get here is 1.2 divided by 0.379, 3.17, then I put it here. Okay, so let's see what value we get. 16 times 1.9 divided by 3.17, 9.59. Okay, so we get this. So let's see why it is different. Basically, it is different because let's see, 3.17. Let's see the displacement over time. Displacement over time at 1.2 equal or not? One 1.9 over 3.17, 0.59. Okay. So do you put 3.17 as the time? Or you put other value?
Yeah.
3.17. So you see how we derive the formula. Force equal to, power equal to force times displacement over time. Okay, so this is displacement, this is the time. So if you want to get 19.2, right, that means displacement divided by time must equal to 1.2, and then you will get 19.2. But when you take 1.9 divided by 3.17, 1.9 divided by 3.17, you don't get the 1.2, you get something else. You get 0.6. You get 0.6. Okay, 0.6. Yeah. This one is 1.2. So what happened is you just get like half of it. Just get half of it. Okay. The the explanation why you get half of it is basically because you see the calculation over here is they start from 1.2 that decelerate to 0, you know. So imagine it's like going down 1.2 to 0. So they are like taking the average. Okay, taking the average 0.6. 0.6. So if you are using this way, you will get the average velocity is 0.6. Okay, this is 0.6.
Yeah.
But if you are using this, we assume the velocity is 1.2 and no deceleration happens, you know. So it's that situation, you know. No deceleration happens. The power when the speed is 1.2. Okay, so then you get 1.2. This one deceleration happen that take the average between the 1.2 and 0. The average is 0.6. Then that's why you get the power to be half of this answer. So that means you must be careful. You follow the questions. Follow the question. They say speed 1 point. Then you don't take 0.6. So if you take the speed of 0.6, of course, different answer. Okay, so that's the reason. Okay, now let's come to C. The trolley now move down a straight slope that is inclined at an angle of 2.8 degree to the horizontal as shown in figure 3.1. So you can see here 2.8 degrees there. The constant force that opposes the motion of the trolley is 16 Newton. Calculate the trolley. Calculate for the trolley moving down the slope, the component down the slope of the trolley's weight. So that means you have to do resolution. Something like this. Going down is W. Okay, W. And we put it in two components. One is parallel with the slope, another one is perpendicular with the slope. Okay. Or you can put in the other way. Normally, students will put in the other way. So this way. So of course it's the same. If you want to use the way that I put just now, it's just fine. Okay. W is here. This is perpendicular to the slope. This is parallel to the slope. So the 2.8 is here. So component down the slope is this one, opposite 2.8. So we call it W sine 2.8. Okay. So in order to count this, we just put it here. Component down the slope is W sine theta, which is mg sine theta. So the m is 42, the g is 9.81, sine 2.8. So 42 times 9.81 times sine 2.8. So we get 20.1. 20.1 Newton. Okay. So now you imagine going down the slope is 20.1 Newton. Opposing the slope is 16 Newton. 16 Newton is the other way. Okay, now let's move on. Okay, so we put the answer here. Component of weight 20.1. Okay, now part 2. The time for the trolley to travel from rest a distance of 3.5 meter along the length of the slope. So we have this displacement 3.5 from rest, u equal to 0. Calculate the time t. So we have, you want to use Shewhart formula, right? So we need 4 quantities. Okay, so we have only 3. So let's use the force to count the acceleration first. So we use the Newton's second law. Net force equal to mass times acceleration to find the acceleration. So as you can see, to find the net force, we have to use 20.1 minus with the 16 Newton. This is the constant force that opposes the motion. So most likely that is a friction. Okay, so 20.1 minus 16 to get the net force. Then the mass is 42, followed by A. So then we get A. So A is 0.0976. Okay, so we have A, we have U, we have S, we have T. So we have to choose this formula. S equal to UT plus half AT squared. So 3.5, 0, half, 0.0976 T squared. T squared unknown. Then we just solve. 3.5 times 2 over 0.0976, and we square root 8.47. T equal to 8.47. So this is the time. Okay, now let's move on. Part D. Use your answer to C part 2 to explain why, for safety reasons, the slope is not made any steeper. Okay, so you see C part 2 tell us to stop the trolley. So we need 3.5 meter. 3.5 meter from rest. The time for the trolley to travel from rest to a distance 3.5. Okay, so you see C part 2, right? C part 2, what we count is if the trolley start from rest, it moves 3.5 meter, it takes 8.47. So imagine if the slope is steeper. If it's steeper, of course, if we move faster, Okay, so if we move faster, then it take a shorter time. To move 3.5 meter. So dangerous, huh? Yeah, dangerous. If it's deeper, then it's dangerous when you can't stop it. So put the reason here. Allow plenty of time to stop the trolley. So if it's too steep, you don't have enough time to stop it. So that's the thing. Okay, so that is how we handle the questions, the whole question for this. Okay, now, yes.
Let's scroll up to part 1.
Yeah, sure. Something wrong with the working. See the right.
Why the keep moving?
Something wrong somewhere. Yeah, part 1.
Can you explain why you draw the triangle like that?
Okay, sure. This D you have done, right? I wrote away.
Can you erase it? Can you erase it?
I think it's back to normal already. Okay. So for C, why we draw the triangle like this? Imagine, if you put an object here, and it make an angle of theta from horizontal. So basically the weight is acting downward. Okay. So you can draw triangle in 2 ways. You see which way is more acceptable for you. But the idea is when you want to find out the 2 component, right? The 2 component must be perpendicular to each other. Okay, so for example, you want component down the slope, right? So one of the way is you do like this, down the slope versus perpendicular to the slope. So this is one way to draw it.
Why is weight the resultant force in this case?
Because they want us to find the component of weight. So that's why the weight be the one that you need to resolve into component. So that's why they call it component of weight. So the weight must be the hypotenuse of the triangle. So that the main concept is like that. You want to find a component of what, then that one will be the hypotenuse of the right angle triangle. This is one way lah. If you don't want this way, right? Sorry.
No, I understand. Continue.
Okay. If you don't want this triangle, right, you can just take this type. You take weight as the hypotenuse again. You take this and this. Okay. So most students they learn from college, they use this way, where if this is theta, then the theta will be here. And then this is opposite, so that's why this is W sine theta. And that is what am I using. Of course, if you are using this way, then the theta is here. then this is still W sine theta. So it depends on how you think about it. So you know already, yeah?
Yeah.
Okay.
UB.
UA minus UB equal to VB minus VA. Oh, okay. This is a tricky question. You see what we learned is, the formula that we learned is the formula written in B, right? But it is tricky because of this. The moment when we learn the formula, right, we have to know that UA minus UB equal to VB minus VA. In the note, we are taking this as velocity. Velocity, yeah. But they give speeds, you know. They don't care about the direction, they give speeds, you see, speeds. So you have to put direction on your own. For example, UA positive, UB, right? You have to put negative on your own. VB positive, VA positive. So at the end, you can get trapped because of that. At the end, it has to be that, and answer is A. So this is tricky. So is that okay for this one?
Yeah.
Okay, remember that, must put velocity in that formula. So they may trap you easily in this way. Okay. Now, let's look at one more question. We try one more. Okay, this one, number 9, on the first page.
The answer is C.
Total kinetic energy before impact is 0. It cannot be, because you see 1/2 mv square plus 1/2 m negative v square equal to, cannot be 0. It's mv square. So from here, you know the answer is B already.
Oh.
Okay, so we count like this to get the kinetic energy before impact. Before impact is mv square. Since they say elastic, so after impact should be mv square also.
Teacher. To calculate kinetic energy, you use velocity, right?
Use velocity.
But velocity is vector. How come when you calculate kinetic energy, it becomes scalar?
You mean when I calculate which one? Kinetic energy?
Yeah, it's kinetic energy scalar or vector.
The V here, right? The V here is velocity. But kinetic energy is scalar. Yeah. It doesn't really matter when even you put speed, you will still get the same answer because of the square.
Yeah, I forgot about the square.
So that's why. Okay. Okay, so B at the end.